Yeah, I would like to thank the organizers for inviting me to this very interesting event. And I also thought what I could present here, because I did not really work hard on the emergence of the classical world from quantum world. Of course, as every physicist, one thinks a lot about this question, but it's difficult to make really very clear statements. Now, I asked myself, what can we say about the structure of quantum physics in comparison with the structure of classical physics? And when you see what the main difference is, then the main difference seems to be that the structure of the space of observables is quite different in the quantum case, because you have this realization of observables as operators on some Hilbert space, and in particular the product of these operators has no direct physical meaning. And the question is, can we nevertheless understand where this product comes from? Now, so what is the characteristic for quantum theory? Of course, one could also look at the space of states, as was done in the previous talk, but I think for many purposes it's easier to start from the structure of the observables. So in quantum theory, we have the observables as self-adjoint elements of an associative, involutive, complex algebra, typically a C-star algebra. And in classical physics, the observables are usually represented as real-valued functions on the configuration space, which is just a space of positions of momentum in classical mechanics, or the space of field configurations in field theory. And these observables, because these are real-valued functions, it makes sense to multiply these functions. This is, on the classical level, something which is completely straightforward. But there is a second structure in the classical case, namely you can express the equation of motion by an algebraic structure, which is the Poisson bracket. So if you have two functions, f and g, on the classical configuration space, you can map this into a third function in these brackets fg, and this is the so-called Poisson bracket, and this has certain nice algebraic properties. One is that it's related to the commutative product just by the usual Leibniz rule for derivatives. So the product fg, Poisson bracket with h, is f times the Poisson bracket of g and h plus Poisson bracket of f and h is g. So this is just the usual rule for derivatives. And in addition, you have a consistency relation, which is the Jacobi identity. So when you make this cyclic sum about the second Poisson bracket, then the sum over these cyclic permutations vanishes. Now, the structure also can be easily understood. Namely, first of all, as I already said, we have observables interpreted as real-valued functions on the configuration space with pointwise defined operations. So we have if we label our measuring values by real numbers, we can just multiply these numbers or add them, and this gives an associative commutative algebra over the real numbers. And the Poisson bracket, which is an additional structure, gives the dynamics in the form of the equation of motion, namely the time derivative of this function is given by the Poisson bracket with the Hamiltonian, which is just a function which gives the energy to the configuration. And instead of the Hamiltonian function, you can use other functions. This gives other continuous evolutions like rotations or translation or whatever you want to do. So this is the structure in classical mechanics. Now what is the structure in quantum mechanics? Actually, you can formulate the properties of quantum observables in a similar way as in classical physics. Namely, over there, when you consider an observable as some device which gives you some measurement results, and by choice you associate to the measurement results some real numbers, which you can do, which is practical. And then you can, of course, change your the real number you associate to a certain measurement result, so you have functions of observables. So also this is very easy, and in particular, you can then see that you can find a product of self-adjoint operators. Namely, you define not the product of operators, but you take the symmetrized product, the anti-commutator. This is this A circle B. This is a so-called Jordan product. Already Jordan, immediately after the invention of quantum mechanics, found that this was an interesting operation on observables. Now there is also a second operation which produces self-adjoint operators from two self-adjoint operators. Namely, this is the commutator divided by the imaginary unit. I also added this H bar, but this is just a usual convention. So this gives an anti-symmetric product, and also this anti-symmetric product satisfies the Leibniz rule, and it satisfies the Jacobi identity. Now there is a third relation which is satisfied by these two products. Namely, this is a relation between the associators. So these products are not associative. For the Poisson bracket, this is also true in classical mechanics, that this is not an associative product. But the product of numbers is, of course, associative. So the product does not depend on the way you perform the operations. You can, for instance, here you can form the composite of A and B and then compose it with C, or you can do in the other way. And for numbers, this would give the same. But here, for the Jordan product, one can show that this product is not associative, so this difference is non-zero. And for the Poisson bracket, or here for the quantum analog of the Poisson bracket, namely this commutator divided by I, you have quite a similar relation coming from the, and can express it in terms of the Jacobi identity. And when you compare in quantum physics these two relations, you find that these two associators, so the associator is just the derivation from the law of associativity. You do it for both products. You look at these differences and you see that they are proportional to each other. And the question is, can one understand why in quantum physics these two associators are related by such a relation? So, but let us first see what happens if we have this relation between the associators. Then we can combine these two products, which have completely different motivations. We can combine them to a product in a somewhat larger algebra. Namely, we complexify our algebra by tensoring it with the complex numbers. And then we define on this complexified algebra a new product, which is just given by the Yaron product times the product of these complex numbers z and z prime, plus related to this prefactor of the second term. So then the question is, can we find a motivation for physical interpretation of this relation? So all the other relations have a physical interpretation, namely the linear structure. The linear structure may be seen as a remnant of the classical structure. So we have numbers for given.
I think the mic doesn't work.
Does not work?
It doesn't. Can you use
yeah. Okay, so the linear structure is, of course, also something which may be not so easy to understand. For expectation values is still valid in quantum physics, so we assume that the linear structure is preserved. The Yaron structure can be obtained from the existence of squares. So as I said at the beginning, we associate to measurement results real numbers, and of course we can square these numbers. There's no problem. And once we have squares of numbers, then we can perform the Yaron product just as a difference of these squares. So we need two ingredients, the existence of squares and the linear structure, and then we can define the Yaron product. Then we have this second product, the anti-symmetric product, the analogy to the Poisson bracket. And this is just a structure that observables have a dual role, not only as things which you can measure, but also as generators of symmetries. And we just assume that the same structure is there in quantum physics. Then we have these algebraic relations, so the Leibniz rule and the Jacobi identity. But these are just consistency rules. If I want to use this anti-symmetric bracket as a generator for symmetries, just the requirement for consistency that the Leibniz rule holds. And similar for the Jacobi identity. So these relations are quite natural. And now the question is, can we also understand this relation between the associators? Now the idea which I want to describe here is that there is an additional constraint on physical systems which comes from the possibility that we consider systems as subsystems of larger systems. So every physical system we look at is a part of a larger system, and it's crucial for the ability to do physics that we can understand smaller systems without making errors. Yeah? So when we look at a physical system, it should be to some extent irrelevant whether the system is part of a larger system or not. In particular, when I have different systems which are independent, I should be able to consider them as parts of a joint larger system. And I want to formalize this idea in the following way. So I have this algebraic structure. Okay, I did not know how to call it because the bi-algebra is already used with a different meaning, so I called it from the physics point of view, because the unit observable represents a trivial measurement, where you always get the measurement results 1. You get only one result, yeah, so you don't have to measure. And when you have independent systems of a larger system, you need the possibility to have for the rest of the system just a trivial observation. Now, okay, now I want to formulate this mathematically. So we have two such, and I have a third Q algebra, capital C, and I have maps alpha from A to C and beta from B to C, and these should be structure-preserving maps, so they are injective, and they preserve all the structures, so both products are preserved, and the units are mapped to units. Moreover, I want this embedding to be such that the two subsystems are really independent. Of course, the question is, what does this really mean, that they are independent? So I use the following conditions. First of all, there should be no new linear relations between these observables. So we embed the observables of the system A and the observables of the system B. We compose them by the commutative product. And this is now a linear subspace of C. And the requirement is that there are no new linear relations, which means mathematically that this is isomorphic as a vector space to the vector space tensor product of these two vector spaces. Then the symmetries induced by the system A act trivially on B, which means that the anti-symmetric product between alpha of A and beta of B is 0. And I require a similar relation for the commutative product, namely, we know that the associative product is not associative, but there are some weaker forms of associativity which should hold. So in particular, when I have a product of some element of A and some element of B, and then it takes a product with some element of A, then this should not be perturbed by the existence of B. So I can multiply A and A prime, and alpha preserves the product, so this is just A times A prime, and here I have beta of B. Perhaps I should have here a circle here. This is the symmetric product here. And the same holds when I multiply with an element of B. Yeah, so also these commutative products of the two systems are independent of each other. Actually, in the theory of Yaron algebras, this relation is, one talks about commutativity in Yaron algebras. So this means that the elements from these two systems commute on the level of Yaron algebras. So this is some weaker form of associativity. Okay, now I have these two systems. I have this embedding as independent subsystems. And to simplify the notation, I now omit these letters alpha and beta, consider A and B as subsets of C, and omit this symbol circle. And I now want to see what I know from the structure of these products of elements of A and B in this larger algebra C, and I look at the anti-symmetric product of A and B. Oh, why should I use, this should be these other brackets. Oh, I'm sorry. This is wavy brackets here. So then we apply the Leibniz rule, and from the Leibniz rule, you can and together with the condition that the brackets between elements of A and B are trivial, you get this relation. So the new antisymmetric product is given by the old one in A times the commutative product in B plus the second term. And so this is something that you get very easily. Now you can try to look at the Jacobi identity. And the Jacobi identity is just the cyclic permutation of the second bracket. So we have here the first bracket of two elements, second bracket, and you then make a cyclic permutation of the indices. And the sum must be 0 because already the Jacobi identity holds also in this larger system. So now we introduce two notations for the associators. So the associator for the symmetric product is written here in square brackets. The associator for the antisymmetric product is written here in terms of wavy brackets of 3 elements always. Yes, always this difference of these different orders in which these compositions are performed. And then one applies the Jacobi identity. Okay, this is a somewhat lengthy calculation, which I cannot present here. But the result is that a certain linear combination of associators vanishes. So we have 4 such terms, and the sum of these terms vanish. Now I use the fact that there are no new linear relations on these products of A's and B's. So when such a sum vanishes, we can draw conclusions for the terms in one factor. Unfortunately, it's here a little bit complicated because there are still 4 summands. So we try to simplify the equation by using some relation. Namely, we look at a special case where A1 is equal to A2. And then one can easily check that these associators vanish if here the first and the last entry are equal. And this holds for both associators. Here it holds because of the Jacobi identity, and here it holds because of the commutativity of the product. And then from these 4 terms we had before, only 2 terms survive. So we get this equation. Of course, here we have now the problem that this is not the most general associator because now 2 of these elements are equal, but neighboring, not on the opposite parts. Yeah? These are equal. So it could be that this becomes trivial. Namely, the question is, can this expression vanish identically? But then we use a further property, namely, we already know that these quantities are 0 if A1 is equal to A2, which means that the associator is antisymmetric in the exchange of the first and the last entry. If this would vanish, it would mean that it's also antisymmetric under the exchange of the first two variables. And so it would be totally antisymmetric, and total antisymmetric means that it's invariant under cyclic permutations. So in the Jacobi identity, you would add 3 times the same number and would get 0, so it would always be 0. So we assume now that our associator is non-zero, at least for some triple of elements in A. And then we conclude from the relation before that the two associators in the B algebra must be proportional to each other, because otherwise this element of the tensor product cannot vanish. And we can, of course, draw the same conclusion if the associator on B is non-trivial, and we get this same relation for the associators of A with the same lambda. And then we can now compute the symmetric product of these elements in the larger algebra C. Namely, we have elements AB multiplied by A prime B prime. We change the order in which we perform these operators by multiplying first with A prime, then with B prime. And then we made some error, which is just this associator here. Now we had some rules for the independence of A and B, which tells us that if we multiply successively elements of A and B, we can absorb everything in the original algebras. So we multiply by A prime. The product by A prime is just the product in the algebra A. And here, and then there remains the multiplication by B prime, so we can get expression like this. But now we have a second relation, namely the relation for the associator. So the associator is proportional to the associator of the antisymmetric product. And for the antisymmetric product, we can just use the Jacobi identity and find that this is a product of these two brackets, A and A prime, B and B prime. Okay, so let me, this is straightforward, but of course it's difficult to follow the calculations in detail. So my message is that also the symmetric product on this larger system is determined by the products in the smaller system. But this combination is not completely trivial because it's a product of the symmetric products. And here you have a multiple of the antisymmetric products. And now we can construct such an embedding of independent systems in the following way. Namely, we take the tensor product of the two systems, and we define now two products on the new system, namely the product where here have the antisymmetric product, here the symmetric one, and here the opposite. And for the symmetric product in the new system, we take this combination of the symmetric products and here of the antisymmetric product. And here occurs this prefactor lambda. So what is the result? The result is that there exists, once we have this relation with lambda, we have such a Q algebra, which I call A tensor index lambda times B. We have these embeddings, alpha, namely A goes in A tensor 1 and B goes in 1 tensor B. And then alpha beta is an independent embedding. So what is the conclusion? The conclusion is the following theorem: let A and B be Q algebras with non-trivial associators for the anti-symmetric product. Then an independent embedding, alpha beta, of the two systems in a third system C exists if and only if the associator relation is satisfied in A and B with the same value of lambda. And moreover, for any independent embedding, there exists a unique monomorphism gamma, which maps this tensor system, A tensor index lambda B, to C, where gamma of A tensor B is just alpha of A tensor beta of B. Okay, so this is this conjecture that the embedding as independent system really implies this relation between associators is correct. And then I asked myself, this is such a simple idea, this should be known. I checked it before, I did the calculation, but did not find anything. But afterwards, I immediately found that this was already done by two people. I cannot pronounce his name, a Croatic name, Gring, and Petersen. But Petersen, actually, he was the last student of Niels Bohr. And he did a lot of work on the foundations of quantum mechanics. And in particular, in a paper which has only 7 citations, he gave an argument which is more or less identical to the argument I just described. Namely that if you assume that you can compose physical systems, you have to introduce this relation between the associators, and at the end you get an associative product of observables. Now, as I said, this paper has only very few citations, but there's some recent work which I found by looking at these few citations, namely by Kapustin and by Moldoviano, where they also exploit this structure. Now there remains a problem, namely, so we have seen from the existence of independent embeddings, we know that we have this relation to associators, and as I said at the beginning, this allows us to find an associative algebra with a new product. Namely, we can distinguish 3 cases. One is lambda equals 0. Then the commutative product is also associative, because the associator of the commutative product was lambda times the associator of the anti-symmetric product. So if lambda is 0, this product is associative, and one obtains the Poisson algebra. So this is a case of classical physics, which is, of course, completely consistent. And but there is a second case, namely lambda smaller 0. Then one can define an associative product by this formula, where we take the square root of lambda, the absolute value of lambda, and here's the anti-symmetric product. This is called hyperbolic quantum theory, and it's a little bit strange. But we have the third case, lambda positive. This would be our standard case. We had in quantum physics lambda equal h bar squared over 4, so this is a positive quantity. And in this case, one has this associative product not on A itself, but on the complexified A. So we have to tensor by the complex numbers, and one has this product which I already wrote in the beginning. And in addition, to find the observables in this larger algebra, you look at those elements which are invariant under the involution, where I take the complex conjugate on the side of the complex numbers here. This is just standard quantum theory. So the remaining problem is, can we understand why the hyperbolic quantum theory does not occur in nature? Or maybe it occurs and we just have not seen it, which would, of course, be more exciting, but okay. So there is a classical answer, actually, namely already Yaron thought about these problems, of course, in a slightly different way, without using this anti-symmetric structure, but just using the symmetric structure. And in collaboration with von Neumann and Wigner, they constructed the Yaron algebras for finite dimensional systems. So finite dimensional here really means that the space of observables is finite dimensional, so like a spin system. And then they added an additional property, what they called formally real. So this is some positivity structure, namely you require that squares of observables are in some sense positive objects, which means in particular when we add them, and this is sum is 0, that this can happen only if both are 0. And then they classified all possible Yaron algebras with this structure, and when they found, okay, they were all known, and then you can look in this family of finite dimensional Yaron algebras, all formally real algebras, and then you can look at this additional structure I have described before, and just this hyperbolic case does not occur in this list, so it is excluded. But of course, this is not so satisfactory from the point of view of physics, because these finite dimensional quantum systems are in a sense very special cases. Yeah? So we would like to find the general case. And actually in the general case also something was done, namely there is even a book by Hanke, Olson, and Sturmer where they look at infinite dimensional Yaron algebras, and they impose a positivity structure in a slightly different way, in what they call a order unit space. So this means the following. So this space is partially ordered. The set of positive elements is a proper convex cone, which in particular means if I multiply it by the positive number, it remains as a set. And if I add two of them, the sum is also in this set. Then one has a comparison with the trivial observable, the 1. So for all elements, you can bound it, all elements by a multiple of 1, yeah, to lower bound and an upper bound. And then there is to exclude certain somewhat crazy possibilities is that you require that this order is Archimedean, which means if you find something which is such that all multiples are smaller than 1, all positive multiples, then this observable must be smaller or equal to 1. Then we can introduce a norm, just as the smallest number C, which satisfies this relation. And then they add in further an assumption. So if the norm is smaller or equal to 1, then A squared should be between 0 and 1. Okay, now they look at Yaron algebras and can classify them. Now, when you now assume in addition, as we found in this hyperbolic case, that we have an associative algebra, then it seems that we can conclude that this algebra is also commutative. There's a paper by Palmer, even older, 1970. Unfortunately, he refers for this argument to some literature I could not discover. So at the moment, I'm not sure that the argument is correct, so I could not really check it. It's only inside some proof that he makes such a remark. And there's also a recent paper by Moldoviano, which gives also argument why the hyperbolic case cannot occur. A little bit different. He does not quote Olson and Sturmer, so it's not so clear whether it's really the same argument. But the conclusion is, so we have the non-commutative product of observables in quantum theory. They should be understood as a combination of two different structures, namely the freedom of labeling measuring results in different ways by real numbers yields the Yaron product and a positivity structure. And the dual role of observables as generators of symmetry yields a Lie product. And the possibility to consider independent systems as subsystems of a larger system yields the associativity of the product. And the last point is that the positivity constraints seem to require the extension to a complex C-star algebras. I'm very confident that this is true, but at the moment I don't have a complete proof for this. Thank you for your attention.